185 degrees Fahrenheit. So here it is.
As an introduction, there are several ways to realize a thermal protection circuit, but in most structures realized in the CMOS process, the methods to predetermine the threshold temperature can be simplified to one structure. Applications of this thermal protection circuit. Thermal protection is frequently required by some integrated circuits and devices, such as power amplifier and voltage sources or regulators, to prevent damage caused by overheating, because operation of these power components may easily cause dangerous self-heating.
About the block diagram and the operations of the thermal shutdown, which turns down at 185 degrees Fahrenheit.
Thermal shutdown is usually composed of a reference output voltage, resistance voltage divider branch with hysteresis circuit, and a load. By using reference voltage, the precise reference voltage from the band gap reference is delivered to resistance voltage divider branch and is divided precisely. Then the threshold temperatures of this protection circuit can be set by this precise voltage, unaffected by process variation and mismatch. The hysteresis circuit is also used here to prevent thermal oscillation. The thermal shutdown circuit responds accordingly to a change in temperature which may harm the other devices and circuitries. The thermistor resistance is directly proportional to the input voltage at the inverter of the CMOS. The input voltage decreases as the thermistor resistance decreases, until such a point that the input voltage would not be enough to turn the CMOS high. This will cause the second CMOS inverter to output a low, approximately zero voltage. With the transistor design of the thermal shutdown circuit, it was composed of a Zener diode, an NPN, and a Darlington pair of a transistor. Since the Zener diode is a positive temperature coefficient, as the temperature increases, the voltage at the Zener increases, thereby forcing the current of the base to switch the transistor to the saturation point until the load will be cut off.
Here to discuss about the circuit design, the anti-spice, and the other. Circuit design of the thermal shutdown circuit composes of two 9-volt DC sources, two inverter circuits cascaded, which are composed of two P MOSFETs and two N MOSFETs, a fixed resistor of 1.2 kilo ohm and a thermistor having a value of 10 kilo ohm at 25 degrees Celsius, which are arranged in a voltage divider configuration. This is a table for the standard RTD and thermistor values. We have used a 10K type 2 thermistor operating normally at 25 degrees Celsius or 77 degrees Fahrenheit, which has a normal resistance of 10 kilo ohms, and that our STD point of 185 degrees Fahrenheit. Its resistance is computed to be approximately about 1.1 kilo ohms. At 77 degrees Fahrenheit, as you can see from the circuit diagram, the resistance of the thermistor is 10 kilo ohms, and the computed voltage across the thermistor, which is also the input for the first inverter, is 8.035 volts. As you can see, the green line represents the input voltage or the voltage across the thermistor, and the load voltage or the output voltage from the second inverter is 9 volts, and as you can also see, the blue line on the graph below represents the load voltage or the output voltage from the second inverter. At 185 degrees Fahrenheit, the thermistor resistance is computed to be about 1.1 kilo ohm, and the voltage across the thermistor, which is also equal to the input voltage at the first inverter, is 4.3043 volts, which is shown by the green line at the graph below. The output voltage of the second inverter, or the load voltage, is 680.3 millivolts, which is also or approximately equal to 0. and is shown by the blue line at the graph below. Here is the LT-SPICE netlist for our thermal shutdown circuit. Shown here is the L-edit design of our circuit, which is composed of two cascaded inverter circuits. On the upper part, you can see the P MOSFETs, and in the lower part, the two N MOSFETs. The output of the first inverter is cascaded and is the input of the second inverter. We have checked our design, and using the DRC, we have found that there are no DRC errors found.
Sa daigdig ng agham, tuklasin ang kaalaman. Halina't lumipad sa daigdig ng isipan. Tayo na sa sinus